Okay, I see people joining, and hello, everyone. Hi, and welcome to today's webinar, sponsored by the IUP publishing journal Neuromorphic Computing and Engineering, which has just released just now a new impact factor of 6.1. My name is Giulia D'Angelo, Marie Curie postdoctoral fellow in neuromorphic active vision at the Czech Technical University in Prague, and I will be your host for today and discussion chair for this session. So today the question is tricky. What is meant by neuromorphic computing? In particular, we will focus on a key debate, simulation versus emulation. So first of all, thank you so much for joining us. It's a great pleasure to have you with us today. And let me please take a moment to introduce our great guests with us today. And I'm very excited to have them with us. So let's start with Elisa Donati. Elisa is an adjunct professor at the Institute of Neuroinformatics, University of Zurich, and ETH, or ETH, Zurich. Ciao, Elisa. We are happy to have you today. Could you briefly tell us a little bit what you're working on?
Hello, so good afternoon, and thanks for joining this webinar. So as Giulia was saying, I'm now an adjunct professor at the Institute of Neuroinformatics, and I work in neuromorphic engineering, and my goal is to actually apply neuromorphic engineering for many applications, mainly on biomedical application. You will see shortly in the presentation. Unfortunately, it's only 10 minutes, but the idea is to really find a way of using neuromorphic for solving problems. So, thank you.
So Katie Catherine Schumann is the second guest for today and is an assistant professor in the Department of Electrical Engineering and Computer Science at the University of Tennessee. So hi, Katie, thanks for being here with us today. Could you please tell us a little bit about your work?
Thanks, Julia. I'm excited to be here having this conversation with you all today. So I am an assistant professor in the Department of Electrical Engineering and Computer Science at UT, and I co-lead the 10 Lab Neuromorphic Computing Research Group here. I focus on algorithms, applications, and software for neuromorphic with a specific focus on evolutionary algorithms to design spiking neural networks. And I also focus a lot on co-design of neuromorphic systems, particularly using application needs to inform what the hardware should look like.
Thank you so much. So let's go to our next guest, and it's Jennifer Asler. Jennifer is a professor at the Georgia Institute of Technology in the School of Electrical and Computer Engineering. Hi, Jennifer, and we are very excited to have you here. Please, can you tell us a little bit about your work?
Yeah, thank you so much for having me as part of this debate and discussion. This is great. So my area would be in programmable and configurable analog, neuromorphic, and other physical computing techniques, which includes a whole range of things that go from device level all the way to building large systems and various structures. So.
Thank you so much. Thank you. Okay, let's go to the last guest, which is Emre Nefci. Emre is a director of neuromorphic software ecosystem at the Jülich Research Institute in Germany. Ciao, Emre. We are happy to have you here. And please, can you introduce your research? Thank you.
Sure, yeah. Thanks for organizing this and all the participants for being here. So I'm interested in neuromorphic computing, basically trying to understand how we can do information processing on a physical substrate. And this usually requires thinking quite carefully of how computations take place, where is information stored, how can we bring it to where we need it in order to do the information processing. And the brain here is an important source of inspiration. And so we do have a couple of more computational neuroscientists at my institute that think about this. But we also work at all levels, so starting from devices, memory stores, all the way to architectures and algorithm through collaborations in our Jülich Research Institute. So looking forward for the debate.
Nice, nice. Thank you so much. Okay, guys, this is a debate. So Today, we will explore two possible approaches to neuromorphic computing. The first centers on emulating biological neural processing systems through the physics of computation and computational substrates that have similar properties and constraints as real neural systems, with potential for denser structures and advantages in energy cost. The first approach is represented by what we call today team emulation, which includes Elisa Donati and Jennifer Asler. They will soon deliver a presentation in which they will outline their perspective and why emulation should be the preferred path for advancing neuromorphic computing. Let's go to the second approach. The other approach is more abstract, relying on the simulation of neural processing systems, on scalable architectures that allow the simulation of large neural networks with a higher degree of abstraction, arbitrary precision, high resolution, and no constraint imposed by the physics of the computing medium. Katie Schumann and Emre Netchi, representing the team simulation, will then present their perspective on why efforts should focus on simulating large-scale neural networks. So I don't know about you guys, but this seems very exciting. So both perspectives are incredibly valuable and also quite different. So today we will explore what each of them brings to the table and how they're being developed and what challenges and opportunities lie ahead. So sit, take a drink and get ready. We are gonna get started. And please, on your right, you can write your questions. So please, you will listen to all of these presentations, and as soon as a question comes into your mind, please write it down, because then they will be responding to your questions. Okay, so ready? Let's start with Elisa. Elisa Donati, Team Emulation, will now present neuromorphic emulation toward real-time embedded intelligence. Please, Elisa, I leave you the stage.
I hope you can see my screen. Something is moving
Yes.
around. Yes. So let me know if something goes wrong with the screen, please. So good afternoon, and thanks for joining us in this debate. As Julia was saying, I'm in the neuromorphic emulation team, and I really hope that there's going to be some nice debate at the end of these four presentations. So, and now I want to give you the idea what, for me, we should move towards more, emulation rather than simulation. So I want to start with something simple. So with the definition of neuromorphic engineering, something very classic, something that started with Calvert-Mead in the late 80s, with the idea of designing event-driven analog or mixed signal circuits inspired by structure and dynamics of biological neural systems. So this was the original definition, and I think for many years there was a lot of research around this topic, and especially in the last 15 years, most of the research was focusing on, event-based sensors and how to process these inputs. However, in the last, I would say, 3, 4 to 5 years, there was really a renewed interest in the neuromorphic engineering. And one of the reasons of this renewed interest is because neuromorphic engineering can provide an ideal substrate or an ideal paradigm, computation paradigm for actually build something that is ultra low power. So, and the reason why I'm saying that is because very recently there was this beginning, this advent of artificial intelligence, and here there is I just show one plot that I found. Is a paper that really is on archive now. It's a recent paper like a month ago, and it's basically showing the energy that is required for this artificial intelligence. When I'm talking about artificial intelligence, I'm talking about large language models, because I think now it's most of the research of deep learning and AI is basically there. And you can see here in this plot the energy that is required for one query with the dimension of the token dimension of 1 kilo in input and 1 kilo in output. Of course, if you have something that is more like 10 kilos, the energy is much higher. So this is what is required for query. So for a long time, when I was discussing with people doing, deep learning, AI, and we were claiming that it's very computationally expensive to do the training, everyone was saying yes, but the training is something that happens once and then it's gone. And even if you look at the training, you can see here that the amount of CO2 that was consumed for training the GPT-3, it was 550 tons of CO2. However, what I'm plotting here is basically the energy required for token. And you can see that if you think for query, and if you think of the amount of query that we have per day, is something that is easily scaled up to an amount of energy that is not sustainable. And this is the reason why now there is this renewed interest in neuromorphic to find an ideal platform or algorithms that they actually can try to solve the problem of the energy consumption. So that's why now I would like to talk about what is neuromorphic computing, because in my idea, neuromorphic computing is something that is it's like the umbrella of neuromorphic engineering. So the neuromorphic computing is a computational paradigm inspired by the structure and dynamics of the brain. So it can even be on simulation, right? It doesn't have, you don't need to have an hardware for doing neuromorphic computing. So the idea is using these spiking neural networks with this event-driven architecture to basically process information. But if we look at this computing and we now forget for a while about the technology and the real hardware, so we can have other characteristics. So the idea is that if we want to build huge network like the one, for example, required for the AI, so we need to simulate millions of neurons. So we need to have this very scalable architecture. And the entire line of research is basically focusing on building algorithm-driven innovation, so something that solves problems rather than really looking at maybe the brain does. Sometimes we can forget about the brain. We actually look at how to solve the solution. And this is, I think, nowadays in the domain of neuromorphic engineering is the main trend. I would say that probably 80%, 8 to 90% of people that now is working on who is now working on neuromorphic computing is focusing more or try to demonstrate in this large-scale AI using this brain-inspired architecture. And for this goal, there is the need of this expansion of neuromorphic computing infrastructure. And I'm sure someone is going to talk about, this cloud-hosted CNN simulator that can be now. We have Spin Cloud, we have Deep South, so we have this huge cloud where you can actually run your SNN. And the idea behind this is basically to push towards scalability. So to have something, this is a 2D huge system where they can actually have this large network. And you also want to have accessibility. So you want to have people able to have the platform to actually run something and try to beat or try to achieve the performance of the deep learning. And again, this is something that since you want to build something that is efficient, sometimes we forget about the biological plausibility because we want to solve something. We don't want to actually copy the brain exactly. So, but for me, this can open some questions and some even challenge, because I'm wondering if it's really true that if we actually have something that is large, if we can actually build something that is intelligent. It's really true that having more neurons allows you to have something that is more intelligent. Can we also build something in closed loop? Because if we want to build like a device that is able to interact with the environment, so we need to have something able to read in real time and react in real time. And at the same time, if you want to do something that is far away from the body, so is it really true? So we have this disembodiment. So we miss the brain and body dyad, right? So there is something that is not connected anymore. There is something that we don't have in our body. That's why my view is something that neuromorphic is something that is more than just energy efficient, right? So if we go back and we think of the hardware, so we can think of really the technology, so we can have an ideal substrate for designing real-time embodied intelligence. So we have multiple advantages. That is not just the energy efficiency, but it's, for example, having a compact device where we can have, again, this co-localized memory and processing, where we can eliminate the memory bottlenecks. Think, for example, of all the memristors line of research, where we can actually build in memory computing. We can have a system that is very fast with a very high reactivity. So because you have multiple neurons with mismatch, so by all of them they have like an heterogeneous threshold. So some of them that can be faster than others, so you can have a very fast reaction. And we can have in the same device, without storing anything, we can actually have dynamics in the order of milliseconds up to the order of hours, days, months, and everything with the same substrate. Just in the way you program it, just in the way you connect the neurons among each other. So, and if you think of something that is not just neural networks, but you can think of something that we also have in the brain, that is like having some substructure, like computational primitives, we can still solve relevant problems with a few number of neurons. So we don't have to go to this large scale model. And this is basically what I do. So I work on neuromorphic application, and in particular, I work on biomedical application. The reason why I work with biomedical application is because I am a biomedical engineer, but also because I think that all the requirements, all the characteristics I described to you is something that you can immediately see in the biomedical application. However, everything I just said, it can be applied to any other kind of application: robotics, precision farming, environmental monitoring, so all the possible applications. So, and now, since I only have another few minutes, I can only show you one example of what I meant of how to use the substrate to actually perform something that is very powerful. This is a very recent paper. It's something like this year paper, and is a very simple network where the idea it was to actually monitor the heart rate and detect the state of the subject. So in which heart rate, which range of heart rate, and how this heart rate change over time. So the idea was to process signals like EEG, PPG, and to extract, decode the heart rate and the state. So, and it was something extremely simple. So there was the signal, there was the accelerometer. The accelerometer was used to actually clean the signal from the artifact. And if you look at what is in the state of the art right now, so there are huge network and very complex network to clean the signal to remove the artifacts. Here, what we did, it was just subtract these artifacts by using an inhibitory synapses. So something extremely simple and very successful. And then once we had this a clean signal, we were sending everything to the decoder. So the decoder is basically what you can see here. So is a bunch of filters. Each filter connected to one neuron in charge of generating spikes, and each neuron connected to another one and to the neighborhood, so the lateral ones, so with the weight and alpha weight. So, but if you look at this, if you think of the classic biomedical signal processing or signal processing in general, so we try to build these filters with a very high order to have something extremely precise. But if you do that here, it's not going to work, the system, because if you have something that is, for example, between 90 and 100 BPM, you cannot see the difference because you are in the middle of the filter. So what we did, it was by relaxing on the order of the filter, having something that is very imprecise with a very large, roll-off. So to have something that allowed to have the signal to go not only in one filter, but in multiple of them. And in this way, we had the distribution of the Fari rate. And by calculating this distribution of the Fari rate and looking at the mean, so we were able to actually calculate the heart rate. And this is something that is very powerful, because what we got with a bunch of neurons, so this system is 6 filters and like 20 neurons, we got something that is as an error of 1 BPM. And the state-of-the-art deep learning methods now has 4 BPM. So this is something to show you that having something very simple, but using the substrate, you can build something very efficient. This you can also continue with like a neural state machine build of neurons, excitatory and inhibitory neuron connected to have something that can store the information for a long time. We measured that we can store an information for up to 6 months without counting the LED and using a battery of 3.3 volt. And to conclude, I just create this table where I want to show the difference between simulation and emulation for me. So when we have simulation, so we have the nature of the model is abstract, right? And the power consumption is not so low anymore, because if you have like simulator, if you have a cloud, you have to think the structure around that. So it's not so low power anymore. However, the accessibility is pretty high because everyone can access to a cloud, for example, but you cannot really work at the edge, or maybe you can partially work at the edge. There are risks for the privacy because you move data around. It becomes problematic to build something that is real time, and there is scalability, and it's this virtual scalability. So you have this virtual system. However, if we work with emulation, so we really have neurons with all the limitations, so noise and the limited number of neurons. However, we can actually exploit the noise. The power consumption is very low. The accessibility is not so good anymore because you need to have like a chip, However, you can build something that is for the edge computing. You don't have problems with the privacy. You can work with closed loop systems, and you still have scalability. But in this case, rather than having something large, you can have something that is distributed. So you can have this physical scalability. So to conclude, the take-home message of this presentation is that, in my opinion, neuromorphic technology is not about precision. It's about being adaptive, reactive, and efficient in the real world. So thanks for listening to me, and I hope to enjoy the debate later. And I think now we can move on with the simulation theme.
Thank you so much, Elisa. Thank you. So I don't know about the audience, but there is a let's say a provocative point, right? The number of neurons doesn't really mean intelligence, maybe. So maybe this will spark some questions. I don't know. Don't be shy, please write questions. You have this great moment to ask them all of the questions that you have. So again, thank you so much, Elisa. So let's go to the theme simulation. So the theme simulation will have for the first guest, Catherine Schumann, and she will present the value of simulation for neuromorphic computing. Please, Katie, the stage is yours.
Thank you. And just confirming, you can see my screen, okay?
We do.
Excellent. Great. The fantastic work, Elisa. Really, really compelling points. So I think one of the things that I come at the field of neuromorphic computing, I come to it as a computer scientist. So it's a way of viewing the ability to use these platforms really from a computing-driven way. So with that in mind, a couple of years ago, a group of collaborators and I worked together on trying to define what a neuromorphic computing system looks like, really from a computing perspective. And we contrasted it with conventional von Neumann architectures and nailed down a couple of key characteristics. One in the operation with massively parallel processing, in the organization with co-located processing and memory, programming via spiking neural networks, communication via spikes, and asynchronous or event-driven timing. So this was a convenient way for us to think about what are the properties of this computer that we are actually going to be working with. Now, not all neuromorphic systems have all of these properties, and as we're debating here, you can define neuromorphic in a lot of different ways, but this was a convenient way for us to think about them. Now, I have just another list here, similar list of properties for neuromorphic, a couple of others that are added in here, like stochasticity in the neurons for noise, and inherently scalable architectures. Now, even as someone who is primarily doing machine learning research with neuromorphic, kind of thinking of neuromorphic as a way to run spiking neural networks and do spiking neural networks research, obviously all of these characteristics are important for that. But then taking that hat off and just putting my computer scientist hat back on, these properties are useful for a lot of things beyond just machine learning algorithms, and kind of straying beyond just taking inspiration from the brain to do machine learning or to better understand neuroscience. If you just look at a neuromorphic system as a computer with these types of properties, there are a ton of different types of algorithms and applications that make sense to run on these systems. So this is things from like graph algorithms to optimization problems to even simulating various processes like epidemic modeling, for example. All of these have been demonstrated to perform well on neuromorphic systems. So there's a lot of opportunity to explore using neuromorphic systems as just computers with cool characteristics beyond just machine learning and neuroscience. So Elisa mentioned in her talk that we'd see some examples here. So here's some examples of large-scale neuromorphic systems, Spin Cloud and Hala Point, which is Loihi's system from Intel. These are both very, very large-scale neuromorphic systems, and in fact are the largest. So here is a chart kind of showing how the neuromorphic computers have grown over time with those two systems that I showed on the previous slide as the top 2 points in that chart. Now, those systems, as I mentioned, have been demonstrated on a variety of different applications. Again, not just machine learning and not just neuroscience, but also optimization and graph algorithms, and have been able to do those very efficiently and often faster than conventional systems. So these systems have focused more on simulation than emulation. Now, a key question associated with this is that currently driven by technology limitations than it is because simulation is inherently better? I think that is something we could talk about. But there's still a lot of value in having these very large scale systems to help us understand what the opportunities are for using neuromorphic for computation as a whole. So some of the key characteristics that I want to highlight for simulation-based neuromorphic systems. One of the big ones is ease of deployment. There is opportunities to use commercial off-the-shelf intermediate solutions to evaluate simulation-driven neuromorphic, including things like FPGAs. So this gives you the opportunity to start playing with these systems in your lab, even if you don't have access to a physical neuromorphic chip. There's also ease of fabrication and use. Most of these simulation-based systems are using CMOS, and they are fully digital. Those are things we understand, so it gives us the ability to use existing technologies to help understand and effectively use these systems. Now, those two are kind of like, those are accessibility-driven characteristics. I think for me, one of the more exciting things from the simulation perspective is it gives us the ability to really explore different biological features that we should be emulating, and more broadly, different computational features that we should be focusing on building neuromorphic systems into for the future. So that really gives us an opportunity to investigate what are these characteristics that we really want to use to enable us to do the computations of interest. And then scalability is key as well. It's a big question in the field of, does something happen at a particular scale of these systems as you reach this 1 billion, 5 billion, et cetera, neuron mark? Does something emergent start to happen? You can really try to start answering those questions with these very large scale neuromorphic systems. Now, I'm on team simulation here, but really I'm on team why not both? So I think there is really an opportunity to have simulation inform emulation to help us understand what are the characteristics we need to focus on, what are the different computational primitives that are going to be of interest, and then have emulation in turn inform how we're doing simulation as well. I don't think this is an either or moving forward. I think it's both. I think there are going to be places where both are very, very useful to the field, where both have their strengths. But I also think they really have the opportunity to help inform each other as well in their design and their operation moving forward. So with that, I will turn it back over to Julia, here again from Team Emulation.
Thank you so much, Katie. Thank you. So Katie said, is emulation constrained by the technology? Let's hear what Jennifer thinks about it, right? So we have again now Team Emulation coming back with Jennifer Asler, and she will present why physical computation is essential for analog and neuromorphic computing. Please, Jennifer, I leave you the stage.
Thank you. Thank you very much. Again, thank you for the invitation to be here and putting this together. First question, can everyone see my screen before I begin?
We do.
Good, very good. All right, so now I'll begin. So my question here is, why the physical computing is essential for analog and neuromorphic computing. Part of this question is because I think we all understand at some level that simulation is useful. I don't, for anyone who's built ICs or designed before, we need some level of digital simulation, or at least certainly digital simulation, maybe other forms of it have been valuable. So there's rarely a question of is simulation valuable? The question often shows up as, well, I could just do all my science in the simulation and ignore the hardware. And that's where I think I'm going to have the conversation. That's where my point's going to be primarily focused. So when I talk about neuromorphic engineering, I could spend a lot of time here, but I assume that a lot of this is moving towards, hey, it would be nice if we could eventually build human cortex, we could build large systems. And certainly, I certainly looked at a roadmap of this. I think it's a very solid paper, even 12 years ago, and I think it's still fairly solid. Looking at there's a roadmap to build human cortex in standard CMOS, entirely standard CMOS, and that becomes amazing when you could imagine it in a fairly reasonable size with 100 billion complex neurons. Really focusing on the physics of the devices and seeing what you can come up with there. And yes, for those who heard me talk before, yes, I would imagine there'd be floating gates and programming, but that's not the main part of where I'm going today. But there's a whole conversation of energy efficiency, and that's actually very well established of what you can do for physical systems compared to digital, sort of typical digital systems. But there's a whole range of additional structures that's possible when you start talking about neuromorphic algorithms, and then you want to be able to take that and move that into the application space. And so this is a well understood and well established concept. So this is the conversations of where we're trying to go. And then the question is, well, should we, to what amount does the physical systems, the physical implementation really play in this situation? So I'm going to make the statement it is essential. And I'm going to sort of repeat a particular theme throughout, and I'll start it right now, is that when you look at digital numerical solutions of ordinary differential equations, analog computing in any sort of way, it's not a solved problem. If you spent time doing any detailed work in numerical analysis, which I've had the fortune to do that in digital structures, it is still a very difficult problem to guarantee solution across all those ranges. But I think there's also been the other part of this is that it will never be a solved problem. And that forces us for so many different cases to say we have to verify physical systems on physical, real valued computing platforms. There's no way around this. And in case you're thinking, well, how important is ordinary differential equations? This shows up in all places in neural networks. It shows up in training of neural networks. And as we dig into the neuromorphic space, we're going to have this. So I don't think there's any way around these questions. Now you might go, that's a bold statement. How do I justify that? Well, there's a whole range of work that's been developed in terms of analog theory that has come out because of the success of a lot of the analog computational structures. We can talk about this in a realistic way now. And on the right side, you see discussions around digital computing, and people who have done a lot of computer engineering will certainly recognize lots of these pieces in terms of also the Turing machine and its ranges of computing. And there's whole fields of numerical analysis, architecture, abstraction. There's a whole different question when this is in real valued systems. But what has come up over the last 10 years has actually been core conversations on numerical analysis and architecture, abstraction, computing models that can actually extend Turing machines over integers into real values. It allows you then to make equivalences across all sorts of real valued structures within polynomial constraints, which is just a fancy way of saying there's a pretty good way to connect everything. And so it turns out it's interesting because you can definitely say it's easy to go from, if I had a digital system, to go into a real value system, a physical system. That's easy because I just need to discretize things. Going the other way, turns out you can only at best ever do an approximation for some cases because you can only ever represent part of those values. And we see this all the time in differential equations where you have finite numerical time steps, and that causes all sorts of headaches and nightmares. One could get very deep on this, but this is sort of get the impression that this is kind of necessary. This is not a nice to have. And so given that this is the case, we have to verify physical systems on real valued computing platforms. That becomes a key piece of this. The nice part is that there are programmable and reconfigurable computing platforms that are out, certainly in the research side. FPAs are certainly ramping up and becoming available in commercialized spaces. So things like FPGAs, but are analog and mixed signal, are now things that you can actually find, and will continue to probably ramp up and scale. And so all those wonderful points Katie had on deployment and ease, sort of ease of being able to field it, ease of exploration, and scalability, all of these start applying. And so we begin to think, okay, this is now possible. I think there's also the sense that there's an absolute need for both measurements and fast circuit simulation. Again, I didn't say that we should get rid of simulation, and so maybe Katie and I are both, saying, hey, there's a place for both. But in this case, I would say fast analog simulation is a huge issue, because if you just look at just a simple structure like here on the right, where I do a simple analog classifier, assuming it's 10 microseconds per transistor calculation for a structure like this, I'm going to need more than 1 trillion transistor calculations for like 100 seconds of data for a very simple analog classifier problem. That's going to take 4 months to get an answer. This is a huge problem and is a huge open question, and probably needs some of both to make this work in some of these places. And so then the interesting question is, okay, so we need to have this physical computation and sort of fast digital simulation of this. We do have the configurable structures in place. We can start to work on this. We build from a theory that works there and also has the precise programmability. You can minimize mismatch. If you don't do that, then everything starts to get confused. But because we can, program things to, 10, 12, 14 bits of precision, not a problem. The interesting question you might imagine, that these are important for scaling for large systems, but you might also argue is like, hey, if I'm using a configurable device that's configurable and programmable, is that simulation? That's a fair question, and maybe that's kind of where part of this connects through. But we need to have things on physical platforms. There's no way around this conversation. And it's important to kind of look at that. And what we find as you look on terms of the computing question, we need to ask all these different parts and components of these different models, one including the analog numerical analysis question, where the analog actually has really good numerics on its differential equations. And making a comment of saying, well, digital is pristine and perfect and analog is bad and noisy is actually very inaccurate. And there are times when you can turn that on its head. I think it's more to say digital tends to be more for things like linear systems, linear system equations, and analog is more for like numerical analysis, is more numerical of differential equations, and those are their fundamental pieces. So we really need both, but I think that the point is to make a strong sense that we cannot get away from the physical computing system. We need both, and it's really critical is that simulation is not a substitute for the physical computing. You cannot afford to do all your science and digital simulation and then just say, well, we'll just like let the people build stuff, at the end when I figured it out. That has been tried multiple times and almost always leads to failure. And so one could go look at program after program after program that has tried this. And it turns out that you really want to do physical computing from the start. And so with that, I appreciate everyone listening to this, and we will see where this goes.
Thank you so much, Jennifer. Thank you so much. Okay, so I see that you guys are playing soft. We need the simulation and emulation. I'd like you to stretch it a little bit more, right? So I would like, and I'm saying this to the audience, please stretch this and ask questions, because we really do want to understand what is better to do, in which situation is better to do what. And of course, yeah, it might be nice to have them both. Okay, thank you again, Jennifer. Let's go for the last guest, which is Emre Nefci. And we are back to the team simulation. And Emre will present hardware algorithm co-design simulation supports better emulation. Please, I leave you the stage, Emre.
All right, thank you, Julia. Well, I'm sorry, just relating to your last comment, I'm just going to go even deeper into we need both simulation
Yes.
and emulation. And you can see, actually, this is the figure on this slide can be the only thing I can talk about today. I'll go a little bit more detail into how we can use simulation to support better emulation. And in some ways, this is actually just an elaboration of what Katie's last slide, saying that we can have simulation inform emulation and vice versa. So as I explained earlier, so I'm interested in using neuromorphic substrates for computing. I'm interested in the machine learning area. And so the things that we do here, so is hardware algorithm co-design, which I think many of us are implicitly doing. So this is really trying to build new computers that take advantage of the physical substrate here given by devices, materials, architectures, and all the way up to the applications. And in this case, taking inspiration from how brains work. There is a lot of injection, at least on our side, of using machine learning principles because we know they work. And so it's easier for us to design algorithms down to the devices, except that we can't just take machine learning algorithms as such because the realities of the physical system mean that we can't just arbitrarily transport information from one place to another. So we need to focus on specific algorithms that could actually run on that substrate. I'm going to talk a little bit more specifically about learning. Learning is something that I've been working on for a long time, and I think it's a good example of where we could use neuromorphic computing. But at the end, I'll also emphasize that this actually goes beyond just learning along the same lines as Katie mentioned. Okay, so about learning, 30-second crash course here. So learning in the brain is a local process that basically was early on observed as two neurons actually spike together. The amplitude of the responses increase, and so this is what you see here in this graph. So EPSB amplitude is really amplitude of the response on the receiving end. And this very simple model of this kind of long-term plasticity, in this case, is the so-called spike timing dependent plasticity rule, which is a local process. Here, basically, the previous two neurons, the orange and green ones spiking together, would result in weight updates, which are positive or negative, depending on the order in which these spikes arrive. With colleagues of Friedman, Zenke, and others, we've worked and developed beyond STDP rules to try to inject some of the machine learning insights here. And namely, one of the problems with STDP is just that it doesn't depend on how good you're at your task, right? Because there's that weight update is independent of the task performance. So what you can do is you basically modulate these updates with some higher level area, which you can see is something like reward or error. Now, why is this interesting? I told you about machine learning perspectives. It's just that these kinds of rules can actually be directly related to gradient descent, a local form of gradient descent, and that's kind of hard to backpropagate in brain, so you need to do tricks differently. This is where the locality comes in. But the take-home message here is that we can actually do gradient, something like gradient descent in synaptic plasticity rules, which are very much like STDP. Okay, now this said, there's a problem, right? If you actually try to build learning systems like this, they generally fail. And they would fail, in fact, on this problem here. It's a nice paper from Josh Tenenbaum saying that if I show you this picture here and tell you all the objects in the red boxes are tufas, you'll find the other tufas in this picture very easily, even though you've potentially never seen this object, although I've been presenting this slide for a long time, so I'm suspecting many of you already know this. And so you see there's one here, there's one here, there's one here. And the reason why we can do this easily is because maybe it looks something like a flower, it has a stalk, a base, and something like a flower bud. And so we base our learning on prior information. Okay. So this is what makes learning really hard in vanilla standard neural networks. So everything I told you about this gradient-based synaptic plasticity just generally doesn't work. And the reasons for this are that basically learning in neural networks requires you to see the data in a random fashion, IID fashion, which is not how we experience the world, right? You just saw a bunch of pictures there and probably sampled the pictures, the red ones, one after another. And learning is very data inefficient. Gradient descent needs a lot of updates if you're starting from a blank slate. And this is something to realize, that if we're doing learning on a physical substrate, we can't just do large batch sizes, and we have to do it in real time if we're talking about analog systems of the type that Jennifer was mentioning. So the real world is slow. And if you take all these things together, the gradient descent is never going to work. And so what I'm going towards is also what I mentioned earlier, is that we don't actually start from scratch, right? We don't learn from scratch. And this is a fantastic book by Sterling and Laughlin here, which nicely explain in the introductory chapter even, how even small organisms really adapted their memory and their bodies really to their sizes, basically immediate environments that they will likely encounter. There's no point for a C. elegans to remember things across days or years. In fact, they might even not live that long. And so the idea here is that let's not see learning as a process that starts from scratch, a neural network that we initialize with our favorite methods, but that we actually initialize in a way that makes sense on the task that we're trying to solve, whether it's heart rate detection, as we saw earlier, or robotics, etc. And so this brings me to the simulation to emulation. So let's build basically systems that can learn in multiple stages, where the first stage is basically offline simulation stage, which you can see in the to use the kind of large language model terminology. It's the pre-training phase, where you basically see a lot of different tasks, and then a second stage where you do your emulation, and so this can happen actually on the physical device. So how would this look like in practice? So one way to do this is so-called meta-learning, where essentially you build into your simulation environment a simulation of your hardware system. I talked to you about learning synaptic plasticity. So for example, we can have a model of the synaptic plasticity rule inside this offline loop. And just to use the terminology that Jennifer was using, so inside these blue arrows, we can have the ODE simulators, right? Whereas this actually simulates a physical system that would be, for example, our chip on the online side. So it's really trying to simulate a hardware system. And there are many different ways where we can simulate this, and it's an open topic, how we can do the best fast simulations of our hardware. And then once we actually go through this two-stage learning approach, we just then take our pre-trained model and apply it to the real world. And this can really lead to learning systems that are much more power efficient, because they don't need to learn much once you pre-train them. They just need to adapt to the real world, learn new tasks. And also, it can help us, in this case, discover new learning rules. So a couple of examples, we've worked a lot on these things, so this is only a subset of examples, but we did this, for example, on the Intel Loihi chip. You train a model on the Intel Loihi chip with internal plasticity dynamics to learn new gestures. And so when you actually go to the real world and you want to learn new gestures, it can learn it in a single shot. It does this using a technique called model agnostic meta-learning, which basically adapts the parameters of the synaptic plasticity rule and the weight initialization. In another case, we have actually applied this to a model of memristor updates. So memristors are memory devices that can emulate, to some extent, synaptic plasticity. But the dynamics that we get, the conductance update dynamics, are actually not exact. And so this is usually problematic, but we can actually build into our simulation how these conductances are updated. And so when we actually learn weight initialization or our synaptic plasticity rule, we can actually mitigate the non-idealities in the devices. And a more recent work that we've been doing here, and this is a little bit of a longer discussion in itself, but what we're seeing in large language models, so transformers doing this, is actually even in the inference phase, there's something like a learning process going on. And so we use this analogy to implement basically this autoregressive transformer that can do few-shot learning here, not of dog images, but actually of MNIST, like so omniglot digits. So this brings me back to my first figure here. So really what I think we need to do in terms of simulation emulation is use the two together at the same time, in the sense that we have this larger loop that's going to do something like an optimization of the structure or like evolve our network, knowing how the hardware works. And specifically, I showed you this in the case of synaptic plasticity. Once we're done with this, we can take that pre-trained model and put it on the hardware system so it can learn and basically fulfill its task much more efficiently. Okay, that's it for my part.
Thank you so much, Emre. Thank you. So by now we have the majority of them trying to say that we need both. We need emulation and simulation working together. Elisa has a bit of a more strong point of view on I do emulation, and maybe I will take it into account also the simulation. So I'm waiting for the questions, but before waiting for the question that will come out super soon, I want to thank you guys. Thank you so much. So now we start with the debate. I hope there will be a debate. So let's see what comes out from it. The first thing that I would like to ask you is, do you have any question to someone else, so to the other team? Something arose in your mind to ask to someone else from the other team? Is there anyone of you guys that has a question before going to the other questions? I see you smiling. No? Okay, so let's see.
I do have a question, but I might ask it later.
Nice. Thank you. No, why not? Go on, please.
I could go ahead, Emery.
Okay.
I'm sure I could throw out
my
one
question
too.
is for Elisa. So you mentioned that analog hardware is good for multiple timescales. I see where you're going with this, but in some ways, a simulation or a digital architecture, a digital system, can actually emulate multiple timescales much more easily, right? So time is actually an abstract thing. It's my clock, right? So do you think analog systems are really the right way of implementing multiple timescales?
I actually think, I actually would like to ask you more why you think that it's easy to do that in simulation. I think Jennifer, she wants to say something. So please, Jennifer, you can start.
Oh, I don't want to take your time, Lisa.
No, please.
So I actually would argue the opposite, Emery. And the reasoning at the opposite is that differential equation solutions, and again, almost everything comes into that space. When you try to do that numerically, one of the classic problems is that if you run it too long, it eventually becomes more and more unstable. Where the analog physical ODEs do not have that problem. And so, in fact, it's one of the interesting wins, and it's one good indication of the better intermediate dynamics on the analog side. So you can actually build analog systems where you have multiple time scales in the microsecond, millisecond, ODEs running at microsecond, millisecond, second, and minutes time frame. I mean, I personally built things like this, and it runs just fine. You cannot usually get away with that in most of your ODE systems without being in a digital sense, unless you're extremely careful. And even then, you're in a very constrained space. So I actually think the reverse. Now, you would make the argument of, do you have the devices that can handle the dynamics over those ranges? And the answer is, well, there are enough that do that. So assuming we're not talking about things more than 10 years in time frame, we're probably fine.
Can I respond to that, Julia?
Shoot.
Yes, and then we will go towards the questions from the audience.
That's why I said we should do this at the end. Okay, so here's what I mean. So let's say I want to have a fast memory or a very long memory, right? If I want to have a fast memory, well, I just, or if I want to change the timescale of that memory, I can just decide when I change my bit on my SRAM. It's completely arbitrary. I can, for as long as my memory is powered, I can keep that memory there, right? Whereas in an analog system, I actually have to build a specific circuit for every time scale, and that just doesn't seem practical.
No, this I don't think so, right? So when you want, you can actually, so the time scale you can build, it is not only a property of a single circuit, it can even be the interaction, among, other, neurons, for example. So the way I build memory is actually the interaction among the neurons, right? So as a population level. So you can build this fading memory, working memory simply using a balanced network, using oscillators. And this, you don't need any new circuits. It's just the way you connect what you have. And then you can think of, you have one neuron, the neuron can work at different time scale. You have a synapse, it's a little bit faster. You can have population. So you can really so you can actually build these dynamics by connecting them. And you can even control them, because you were mentioning that you can use a bit to actually change your memory, but you can actually, similarly, you can do in our circuits, right? So you can have some control factor, you can raise that to your memory, you can do anything on chip without any, by using inhibitory synapses. I mean, maybe I'm going into details, it's not so relevant, but yeah, you can actually do everything with the circuits that you have.
Yeah.
Okay. Do you want to respond, Emre, super quick? Or you're okay?
Yeah, well, then I'll just respond then. SRAM is basically just a handful of transistors for any length of memory, but I think we're not talking on the same level here. So let's just move on.
I think so we are.
Okay, so I block you guys. We broke the ice. Nice. It was what I wanted. Okay. Now let's go to the first question from the audience that has been received during Elisa's presentation from Amirali Hosseini. And sorry, guys, if I don't pronounce it correctly. I'm trying my best. When the brain plans to perform a task, it extracts the relevant features and prioritizes actions, even in dynamic environments. How can we replicate this behavior in neuromorphic hardware using low-power design strategies, possibly leveraging memory stores for efficient feature extraction and task prioritization?
So it's a long question. So I will try to, I don't want to talk about memristor because I think the point is also something you can do with CMOS, honestly. But actually, I kind of agree with the part of the feature extraction. It's true, right? So, and it's probably everything is, I don't know, today I only had 10 minutes to present what I do, but actually most of my line of research is to kind of extract some features to actually have an easier than processing phase, like decision making, to actually get rid of all the learning that we can have. And this is probably my next question for Emre. But so something like, so what I'm trying to do is actually, if you can actually have a system that is able to extract features, and this is something you can easily do, not easily, maybe not, but you can actually do at the circuit level. You can actually do really at the population level. So you can extract multiple features by some pre-processing with some circuits, filters, and everything. You can think of neurons and synapses as filters, but you can even extract some dynamics or some distribution by using population to extract some particular features. Once you have some kind of features, the one you want, they can be different depending on your feature extraction methods, then you can have this processing phase that, in my opinion, is going to be much easier because you are in the feature domain rather than the signal domain. And then you can do that in the hardware, so directly into the neuromorphic substrate. I think this is part of the question. I don't remember the entire question because it was too long, but yeah. So
guys, if you want to add anything that you think is important, yeah, let's go.
Yeah. So I was just going to say, I think definitely, and it's a lot of the work that our group does too, is you do some kind of feature extraction on the front end, but the challenge is often like, what are the features that are relevant to the problem at hand? And it's not necessarily known a priori, like when you're going into a task, what are the features that are going to be, particularly in a dynamically changing environment, how you're going to actually extract those features out. And so then that becomes all right, well, then how do I adapt or learn to extract the appropriate features that will then make my processing easier? So I think that's part of the challenge of identifying, what are the right features, and different circuits will be needed to extract different types of features. And so I think, yeah, there's a huge question there.
Does anyone want to add anything?
Yeah, I can quickly add something to that. So one particular way to do it is, I mean, if you have an idea of the domain of problems you want to solve, then you can kind of train a system that can learn how to extract features relatively quickly, really in line with what I was discussing earlier as the meta learning problem. The challenge that I see here in doing this is that in order to train a system that goes to feature to actions, so inputs, sensory to actions, you really need to build in a model of your world, right? So how is that action going to change back your sensory? And so closing that loop in a simulation in a faithful way is actually hard. This is a real problem that many roboticists
So if I may, I actually have the opposite idea. So I think one of the using the approach that we have is that, I mean, I agree with you with that you need to, if you know your problem, you can kind of extract the features. But about the model, I think actually you can have a completely model system because you can rely on some kind of adaptation, right? So you don't, actually, if you think of the classic model base, you don't need to know everything about your system. You can actually adapt to something that you have. So it's probably model free what we do, or what we can do model free. So, and actually something that I'm also working on recently is also this idea of having this end-to-end system going from the sensor to the actually then, you know, I don't know, action. And this is something that since it's an entire block, it co-evolve depending on your different sensors and depending on what the action you want to generate. So you can have this evolution of the entire system because it's an end-to-end. So if you think of the system as something that is modular, probably not. But if you think to end-to-end system, then you can actually have something that's it evolves. It's completely model-free. So if you change something in your input, you can your system is going to evolve depending on different sensor, different location, or something like that.
No, actually, if I can just respond to this, I agree with you. When I said a model, I didn't mean like in this reinforcement learning sense of having an internal model of the world. I meant how an action taken is going to affect the sensory processes. So basically just closing that loop inside the simulation environment, which I think is necessary if you want to train these features. If you want to handcraft them, I think that's another story.
Okay, I stop you guys. Let's go for the next question, which is received during Katie's presentation from Sandy Fong. Concerns that are commonly raised with computing with physical substrate is that long-term robustness reliability of physical system, and these physical systems are often not empirically defined, limiting developer to program it. With simulation, one can consistently use any nonlinear math system. So how the emulation team thinks about these? Okay, so this is during Katie, but please go, guys. Who wants to go?
I can jump. Well, I'll let Katie go first.
I will just quickly say, I mean, I think this is one of the advantages to use simulation to inform emulation is to help us understand like what are the dynamics that we're going to need in an emulation, like, but to be able to explore it more fully and help inform, like, it'd be really cool if we had a system that did have this level of reliability. We would need it for this application, and we can show in simulation we need it for this application, and then use that to drive innovation on the emulation side. Yeah, sorry. So I will step back now.
No, that's good. Very good point. I would argue, the first comment is I think there's a misunderstanding that physical systems are necessarily not robust over long time periods. I think there are many that are, but there are some who are quite reasonable and quite good. When we look at questions, and I will certainly say this has a floating gate circuit bias, but it's all standard CMOS, it's beautiful. When you do it, it turns out that it, you have things and they program it in there good for 10 years. We can talk about all sorts of temperature, insensitivities. We can talk about all sorts of other things that work in those circuit elements. So I think the robustness question really depends on the physical system that you're working with. but there are ones that are actually quite robust and have worked for more than 10 years and are still being used. So I think that's the first thing to kind of look at that. I do agree that simulation can help us with understanding, like, what kind of limits and so forth do we need. I think the counter a little bit is that we actually have physical systems that are reconfigurable, so we could actually use physical systems to ask the question. And so it's probably a mixture of things when it's all done, although it may also go to that same line that I had at one point to go, at what point is it simulation, even if it's a reconfigurable physical system to do it? So that line probably gets blurred. So I'll leave it there.
Thank you. Is anyone else want to add anything? No? Okay, so first thing first, I warn the audience that probably it might happen that I will not read all of the questions, so I will try to do my best to block them and get to the end of all of the questions. But let's continue with the debate with the question that is received during Jennifer's presentation from Nimrod Kruger. There are two aspects of neuromorphic computers that are still missing. One is levels of abstractions, and two, performance metrics. Once these two aspects of the field will be solved, Catherine's vision can be achieved, and this entire debate becomes somewhat obsolete. Strong question. Simulations from design neuron hardware, emulators for real-time embedded processors and large-scale systems. How do the panel members see the progress in development of abstraction levels and performance metrics? Okay, I'm happy I don't have to respond to you. Guys.
So I'll jump in and say, I think we're still grappling with abstraction levels. I think that there's so many different questions about, like, yeah, what level of biological inspiration do we need to drill down to give us the computation that we're interested in seeing? And I think that's a neuroscience question as much as it is a neuromorphic question. And then how can we then abstract up to these higher levels that could help us define what the hardware is going to look like? All of that to say, I don't think we have a good, at least in my opinion, I don't think we have a good answer to the abstractions question yet. I think we're making progress on the metrics though. This is where I'll say, I really liked Elise's point. I'm sorry, I can't, I'm not good at being combative. I really like Elise's point on the energy efficiency is not the only thing that we should care about. I think the field is starting to consider these other metrics that we can pull in associated with real-time operation, things with resilience and robustness that all start to come into play with defining, like, the overall performance of these systems. But with that respect, it also depends on the applications that you're targeting. Yeah.
Can I just jump in, just saying why you say that we're getting better with the metrics? Expand a little bit on that.
Yeah, I mean, I think there was a huge focus on energy efficiency as the only concern for a long time from like my perspective, as that was the reason people should be interested in neuromorphic. And I think now, as we're demonstrating more and more of these applications where we're able to show where neuromorphic can have an advantage, it's not just energy efficiency anymore. There are these other factors that come into play where we can say, hey, we actually can show an advantage in terms of speed, potentially. And, it depends on the application. We can show an advantage in terms of resiliency or privacy preservation, security concerns. Like, there are these other areas in which we can actually say, neuromorphic can help here. And so I think from that perspective, we're getting a little bit further on metrics. On what we're measuring those metrics on, that's another question. But I think the metrics we're starting to get a handle on.
Thank you so much. It's difficult for you to debate, guys, but it's difficult for me to be impartial. Jennifer, please.
So a few things. I will certainly say that there's many things besides energy efficiency, although I will still make the argument out as being one of the people who pushed the original comment originally. Energy efficiency is still a big deal. So I don't want to lose that, but there are more things than that, no questions. But I'll leave it there. I think there's an interesting conversation when you look at the difference between analog computing and neuromorphic computing, which analog is more sort of based on, you have more traditional kind of algorithm structures to it. You actually do have levels of abstraction that are getting pretty well defined now. And I think that's a fair conversation. And that comes from understanding concepts of sort of the fundamentals of the computing. And you're getting a pretty good sense of level of getting even metrics now, and getting to the point of, I can talk about realistic, say, metrics and benchmarks that are tied to what the computing does well. That makes sense. Now, and I say all of that because when we get to the neuromorphic computing, and I think this kind of amplifies what was said in a different way, is that part of it is we don't actually understand well what's going on in terms of the computing question. You ask a computational neuroscientist, how does this compute, what is this useful for computing? And you get blank stares. That's not what they do. They're there to say, I'm going to take this and it'll equate to a model and equate to another model. And the problem is that's its own sort of closed ecosystem. And until we sort of break from that to say, what is the computing being done? And by the way, that will probably have an impact on the computational neuroscience, and probably will have very heretical opinions, which has already happened over the last 25, 30 years. That's probably going to be the thing that gets us to understanding what's really being computed. And from there, all the rest of the material comes into play. But it's really the fact that we're so tied to the computational neuroscience side of it. And how do we kind of help either pull that or break away if we have to, while still being faithful to the neuroscience?
Thank you. Guys, do you want to add anything? Otherwise, we go. Yeah, please, Elisa.
I'd like to make a comment about what Jennifer said, because it's true, Jennifer, that it's important, the low power, and it's going to be definitely one of our main advantages, but I really not would focus on that. Because if we can see what it is now in the ICCR, new chips and everything, what they can do is quite impressive. So the low power is pretty low, especially for application oriented. I mean, I work with ECG, EMG, they can beat us, I can tell you. So from the power consumption point of view, and even from new design about this memory design close to the processing, they can do something that is quite advanced right now. But there are some stuff that I think we are better. I have to admit that. For example, something like latency. So what we can do with our system is definitely, for the latency point of view, what we can do is faster than traditional, processor, even, new advanced processors. I would not just only focus on that's what I wanted to do with my presentation, is we shouldn't focus on and only claim about low power. So we can do, I think we are even more competitive in other, metrics like latency, for example.
Okay. Anyone want to say anything on latency? Otherwise, we go on with the next question.
That's good.
Okay, let me find it back. I saw Jens. Let me get there.
Oh, yeah.
Ciao, Jens. Okay, so it has been received during Emulation presentation. So doesn't the solvability of digital ODE orders depends on the required precision? Couldn't you argue that some digital ODEs can be solved to a certain precision? If a simulation is an approximation of a physical system, how are they computationally different? Couldn't you argue that a simulation is an imprecise emulation? Wow. Couldn't be a continuum? That is, emulation and simulation exist on a continuum rather than being two discrete methods. Please.
Actually, I'm thinking this question was more during Jennifer's for Jennifer's talk.
Yeah.
I would defer to Jennifer and build on that.
I'm happy to say more about that. If that's helpful.
Please go on.
There's different questions about it. I mean, obviously, again, as soon as you start talking about, I've got a configurable physical system and I can do that's reconfigurable. Maybe I'm simulating something with that system that is what I really want to build. So in which case, from that perspective, maybe there is a continuum there. On the other hand, there's a whole set of problems in differential equation solvers that are straightforward to find. In fact, if you were to, people in our community would know about simple winner-take-all circuits like John Lazaro type circuits. You can actually set those circuits up with 2 inputs, interesting but physical initial conditions, and the circuit, and you do a very good stiff ODE solver, and it'll still explode to infinity. So if you say it's an approximation of the world, infinity is not an approximation of really anything that's physically working. So there is a place where you have to be careful of that balance. There is something very amazing when you put stuff in a physical system with basically infinitesimal timescales that really keeps things under control, where you can't get the error bounds in other ways. But I think that there are a continuum of questions or continuum of problems, and clearly we need to be able to do good digital simulation, because a lot of times that's where a lot of our tools start from. And then there becomes a continuum. How much of that can we roll out, and whatever we can use to get there faster is what we want.
Thank you, Jennifer. Do you want to add anything? Otherwise, I have another question for Jennifer. Can I go?
I would just, yeah. I would just say that in case the question was really for during my talk, that we really rely on this continuum from ODE to the physical system, right? In the sense that if we want to train a model of our analog hardware, right, we need to do this in a digital way in order to really scale that training. And it's possible that we might, if we just use the digital solver, we would actually latch on to artifacts of the solver, which is not good. And so in that case, we'd have to basically refine that simulation. So I think it really relies on this continuum.
Thank you so much. So let's go on, and we have a question from Rodolphe Sepulcre, and it's a question to Jennifer. So, good point about physical versus digital communication, but isn't there a danger to promote neuromorphic computing just as analog computing? Isn't it there something more specific than analog computation in neuromorphic computing? For me, the promise of event-based computation is to get the best of the 2 worlds, analog versus digital, rather than moving away from digital to go back to analog.
Yeah, I can definitely speak to that. So obviously the first thing to acknowledge is that anytime we do neuromorphic computing, there is plenty of analog structures that exist, even if I'm thinking about events. The minute I look at dendritic infrastructure, the minute I look at things that are going on inside of the cells, it's extremely analog and a tremendous amount of things there. I would say that, yes, there's a clear difference between sort of traditional analog and physical computing. And in fact, if you kind of look at kind of how we started to talk about the differences between the two, it's kind of acknowledged that it is. But many of the neuromorphic concepts are built on what analog has done from a physical computing standpoint, and then you can build and go forward. In fact, one of my classic definitions of how I think about neuromorphic when I'm building it is what algorithms can get better than what I can get in the analog typical analog computing infrastructure. How do I improve past that? And that has often been a very useful way to think about it, because analog computing is factor of 1,000 or better in energy efficiency, and I'm going to use that metric. There's other metrics, but we'll go with that one. And I'll still hold that that's true, even with some impressive things people digitally do now. But it's true in other metrics too. But you begin to realize the neuromorphic side has even more advantages going forward. I think that's true across a whole range of different possibilities there. And so I think you have to at least utilize all the tools you have to get much further on things that would then be both analog and event-based, but it's still going to be analog because it's going to be continuous time typically. At least you try to be there, and as you try to build up the rest of your infrastructure. So I think it's a step in that direction that's necessary as you go forward.
Thank you. Guys, do you want to reply? Do you have anything to say? Otherwise, we go on. Okay, so we get a question that is received during Emre's presentation, but I don't take responsibility if it's towards Emre. So we have a question from Kashira Menes Sendre Alam Shaikh. There are studies showing specific neurons firing in response to abstract concepts like Jennifer Aniston. Amazing. Could insights like this shape how future neuromorphic chips represent memory or meaning? And does this suggest we might one day build chips that encode concepts in a similar, efficient way? So what an occasion to talk about the Jennifer Aniston cells. Please, guys, who wants to start? I'm gonna smile.
Okay, so I'll jump in. I think we don't. I mean, I don't think we necessarily know that it's a single neuron, right? That's encoding. I think it was the grandmother neuron, not the Jennifer Aniston neuron, but but that there is more of this distributed representation, and I think this is coming back to like we have a certain amount of information at a certain granularity from neuroscience, but it's not necessarily, we're not getting the full picture necessarily always with these neuroscience results. And so I think we have to, from the neuromorphic perspective, I think we have to take them with a grain of salt about how we actually incorporate these different features in, because I suspect that there is more of like a distributed representation that is capturing these like specific concepts or memories. However, it would be great if we could store a single value in a single memory within a single neuron. That would be super efficient. I'm just not convinced that that's the way the brain does it.
Yeah.
So building on Katie's response, actually, so I also don't think it's a single neuron that does this, but there's the theory of sparse coding, Bruno Olshausen and field, that really show how representations can be either dense or completely sparse, Jennifer Aniston, or something in the middle, right? And that something in the middle is where the interesting stuff is happening. So sparse coding is a method of doing this, which basically adds robustness to your representation. If you kill a neuron, other neurons would actually take the place and replace and store that concept. And this is recently, in the form of sparse autoencoders, also being used to analyze large language models and see how the concepts actually formed in those large language models. Now, I'm not necessarily saying we need to do large language models in neuromorphic hardware, although there's something interesting there possibly, but that the sparsity, the sparse representations that are not single neurons, but of a dictionary, as a dictionary of neurons, is actually much more what you might be looking for in terms of concepts. Yeah.
Does anyone of you want to add anything? Otherwise, we have another question. Yes, let's go on. So we have another question received during Emre's presentation. I think, Emre, you inspire people to get a question from Giacomo Indiveri. So you can only simulate what you put in the simulator. How can you learn new computational principles that might emerge inadvertently from physical computing substrates if you do not know about them a priori?
So if I can add something.
Yeah, go, Elisa, yeah.
I think Katie was kind of referring to your presentation because at some point you said something about having millions of neurons and seeing emerging behavior. And I had exactly the same question of Giacomo. Maybe we work too close, I don't know. So, and yeah, so that's exactly, I think I have the same comment of Giacomo actually. So,
but
Well,
I think that was Katie's.
yeah.
I
I will feedback. I mean, we don't know, right? We don't know what the dynamics are that are going to emerge at these large scales. But this is precisely why I had that arrow feeding back from emulation to simulation. Is I think that there's opportunity to pull in the dynamics that you're seeing in these physical systems into the simulation. To be fair, you're not capturing necessarily all of the nuance associated with it, but to then help understand, what happens when you do integrate these systems operating together at scale. How do they interact that you may not be able to do physically? Is the simulation actually capturing what you would see physically? Yeah, we don't know, but it could give you a direction to explore. It's maybe worthwhile to look at how these large scale systems interact together. So I think it's a point well taken that we don't necessarily know on the simulation side what we should be simulating. But that's exactly why I had that arrow feeding back, is like, I want to take inspiration from you all as to what we should be exploring in simulation. And I'd love to put some optimization around it to see if we could tweak how they're behaving and see if it changes anything.
If I
Any
can
other
answer
insight? Yeah, please.
yes. So I think that's a very good point. And also, I mean, we need to have a good simulation of the hardware for anything that I described, or maybe Katie described, to work. But there's also an opportunity here to say that, well, our model is not a deterministic model, it's a stochastic model. And that stochasticity, so that distribution, can take into account the non-idealities that we observe in the hardware. So this is where emulation is necessary to actually build the hardware, measure, so what is the kind of distribution of different hardware responses that we get, and then to try to build this in the simulation. That's very possible. And I think it goes both ways. So we need people like you, Giacomo.
Okay, so let's go to the next question, which is received after all of the presentation from Vinicius Scala. So, to what extent can hardware emulation truly capture the emergent properties of biological neural networks? If a neuromorphic chip doesn't capture the full range of biological processes like ion dynamics or glial activity, wouldn't it be more accurate to describe it as something like hardware accelerated simulation rather than a true emulation? I saw Elisa moving the hand.
No, I mean, I was confused by the words accelerators, right? So it depends on the hardware you're using. So if you use, so here, what I use is not accelerated time. So I would not call it accelerator. So I would say, I don't know, platform or tool, but because what we build is a real time, right? So the time, going back to maybe the definition, it represents itself, right? So it's not accelerated. So the question is, I think honestly that it's almost impossible to completely replicate the brain, right? So for many reasons, because also the substrate is not exactly the same. So I think we can emulate many computational principles or many dynamics, but if the goal is to reproduce a brain on chip, this I also think is not something that it can happen, right? Also because the brain is also something is gonna co-evolve with the body. So different animals, they have different brains, so it's difficult to build a brain. So I also don't know which kind of brain or which animal. I mean, it's really something. It's at the same time, I think we can still do a lot. We can still kind of emulate most of the computation, or this way of computing sparsity and I don't know other primitives that it's probably enough to build a lot of cognition and intelligence. I don't know. I don't want to do something wrong when I say intelligence, but yeah. So this is I don't think it's possible. Yeah. Jennifer?
Please, Jack and Jennifer.
Yeah. So I think that I think this is where you lean more on the continuum in terms of all the way from digital simulation through what do we mean by emulation? Because at some point you say, I'm building something on a physical system. I am, in some sense, even though it's a physical system, it's still programmable, configurable, and I can then say, well, it is an approximation, which is what we mean by simulation at some point. It's an approximation of the system. Now, it can be very good in a silicon system because many of the dynamics are actually quite close in neuroscience. We can go from a channel level, that definition is extremely well understood and extremely close. There may be other places where it's less so, but you're still, at some point, there's some level of modeling you're doing. There's some level of approximation, and so all the way through this, there's a continuum in this place. So that's fair. You know, at some point as a scientist, you have to decide where are you on your modeling approach on this. And so that's where I would go with it.
Thank you. Okay, so if anyone else wants to add anything, we go to a question from Dylan Moore. Can I go? Okay, so this is for team emulation. How do you reconcile a need for scalability with the need for neurons and synapses to each be physically instantiated in an emulation system? Simulation digital systems are easier to scale by multiplexing neurons over the physical substrate. Do you think it will be possible to deploy emulation mode analog systems at volume without needing on-device adaptation or learning? I'm thinking about the uncontrolled device mismatch across devices and between chips. Is any of you that wants to start, Jennifer or Elisa?
There was a lot of different comments said in that discussion, so I was trying to make sure that I caught that. So a few things that come into play there. I'll go with the ending points first. There's this interesting assumption there that everything is related, you know, there's a whole set of issues on mismatch and so forth. And again, that's going down a space of some hardware does it, but not all does, and some is actually pretty good. So I think that's probably not being quite knowledgeable on some of those parts, or not including that. I think the conversation on scaling, again, I think is a question of how, you know, there's obviously a whole discussion how you do digital scaling of systems and how do you do analog scaling of systems. There's probably more knowledge known how do you make bigger and bigger digital systems. But fundamentally, you can certainly ramp up and make much bigger analog systems as well. There was the comment about multiplexing neurons, and I would certainly make the argument that that's interesting until you realize that the minute you start seriously multiplexing things, there's a huge amount of complexity cost. Obviously, if I was going to go on energy efficiency, I would say you lose big time as soon as you do that. And you're also losing all the continuous time properties in the process, and that is often very critical for the dynamics that you're trying to build and emulate and understand. So, and I think there's probably some other issues too as well that probably fall into the latency questions and on and on. So I think this lends you into an architecture question that you often see in analog architectures, much the same that you have the architecture question in digital systems. And it's not obvious that the digital is inherently better from that, and we could really start to splice that down on those questions if we wanted to.
Thank you. Elisa, do you want to add anything, or even Andre or Katie, if you want to? Okay, so I need to warn you that we have 6 minutes to the end. So we got a bonus of 10 minutes. So we get 60 minutes to the end. Let's go on. So the next question is from He Zhang. Good evening. Thank you for your time and for the webinar. Thank you so much for being here. I have an open question. Can neuromorphic computing play a role in quantum computer? Ooh. Who does want that? I can't respond, guys. Even if I knew it, I can't respond. Do you have any small hints? Yeah, please, Jennifer.
It's an interesting question. I think one of the things I showed briefly was the fact that if you look at anything it turns out that anything in physical computing, you can talk, any sort of domain in physical computing, you can talk about how do you transfer that to another domain. And so it turns out there's different ways, different implementations, but all of those can be kind of effectively looked at as a way to emulate or build one versus another. So I think that there are some ways to look at it. I think you have a much better play in the short run with some of the more traditional analog techniques on this, but there's no reason that you couldn't ask, are there equivalents and directions there? There's nothing particularly from a fundamental computational level that you couldn't do for one versus the other. And so it makes sense. You should be able to pull this, you should be able to do something there. Do I have an explicit answer? Not off the top of my head for neuromorphic to that, but on the analog side, we could get into that if one wanted to.
Thank you. Okay, so let's go. Yes, Katie.
I was just gonna say, just briefly. I mean, there've been like algorithms that have been mapped to both, like specifically like quantum annealers and neuromorphic. So I think there might be opportunity as we're pushing neuromorphic algorithms to like also maybe apply some of those in the quantum space and vice versa. I think there's, to Jennifer's point, that there's some sort of like mapping that you can define between these two to say, okay, maybe I can start to take some of the computation that I'm learning how to do in neuromorphically and map that into a quantum realm.
Thank you. So let's go to the last question, which is very long. And I have a strong Italian accent. So the question is from Afolabi, and it's saying, from both sides, it sounds like the simulation team, is saying camp, seems to support digital computing to explore neuromorphic or machine learning ideas, while the other side is focused on analog hardware and computing as the primitive for numerical computation. I would appreciate if the panel could address the question of specific application where they believe one approach, analog or digital, should be better. For example, implementing neurons with STDP, neural networks with or without online learning, etc. To also clarify, I don't expect one particular answer, but I would love to hear the nuance of each approach from the panel. Okay, so much more application point of view. Yes, Elisa, I saw you saying something.
I would start saying that since I work on application, I think more of applications in a sense, like rather than having like a neuron with STDP, that to me is not really the application, it's just like the methods of the tool. So if I think of something like application, I think, I don't know, a watch to monitor something, or some device. And the reason why I do analog is because I have access to it's because I actually think that, I work with low bit resolution. And if you work with this low bit resolution, so I think that, for example, analog is much better, the way to go rather than digital. And this is something that I also can kind of, in my goal, long-term goal, I can even think of having something that I can customize, so something that I can make pretty, small. Thinking of, this low bit resolution, you can even have systems that they are kind of even more low power. So then having analog versus digital, it's better to have, if you want to have something that is low power, it's better to go analog. And what else I can say? I don't know, if someone can jump in, then I can continue. I can think of something. Yeah.
So I will just say, I mean, you had it in your slides as well, but I kind of see the like edge versus large scale is the two, like a potential dichotomy. Like I do think that kind of the analog, these emerging devices, you have a lot of opportunity for very small, very efficient, meeting your application needs at the edge. Whereas with these, maybe digital large scale systems, you have the opportunity to explore and do this kind of very large scale computation where you have fewer constraints. Those are sort of the dichotomy. Yeah, Julia.
Okay, guys, this has been incredibly exciting for me and difficult again, because I had to be impartial completely. So I thank you so much. I thank IUP Publishing Journal to have sponsored such a nice webinar debate with you that, of course, you are the expert, the leading expert of neuromorphic, and you're teaching and keep teaching us lots of things throughout the years. So thank you so much for being here today. Thanks to the audience, and please, the audience, tell to everyone that was here and had to go away that this will be fully, it's recorded, so they will be looking at it later if they want. Again, thanks a lot and have a good evening after wherever you are. Thank you.
Thank you
Thank
very
you.
much.
Bye-bye.
Thank you.
Yeah.